Let us talk about volume of revolution. I downloaded this image from a site called UBC Engineering. Now, here, what we have is a graph, part of the graph of a function. Let us say that this is part of the graph of a function. Here it says z equal quarter y squared, but what we're going to do is ignore this and let us say our function is y equal a function of f of x, alright? It could be x squared, it could be x cubed, anything. This is part of the graph of it. Now, you have your x-axis and your y-axis. This is a 3D diagram showing x, y, and z, but we're modifying it for our own purposes. Let's say this axis is our x-axis and this axis is our y-axis. Now this is part of the graph. Now we take that graph and we rotate it by 360 degrees. In other words, we make one complete revolution. What you're looking at here is a cross section of the shape that would be formed. What you would have is a solid being formed. Alright? Now, we want to find out the volume of that solid. What we have here is a radius from the center to the circumference, the radius, and then the distance from where we start to where we stop. Let's just call it dx, a difference in x. Alright? Now, the cross section here we're looking at, if you look straight at it, what you would see is a circle. And the area of this circle, remember the formula for the area of a circle? It is pi r squared, where r is the radius. Alright? Now, if we consider this and say we consider slicing this shape, we get this. In other words, the shape that we would get from the slice would look something like this. Now, over here we have a larger radius than over here. Alright? But let us say that they're close enough to be considered the same radius. And then this is a difference in x. Let's call it dx. Now the thing is, the volume of this, let's say it is a cylinder, it's approximately a cylinder, because if we assume the ratio, the radius on this side and on the next side are the same, it's a cylinder, volume is pi r squared times the height, h. Remember, volume is pi r squared h. But in this case, our h is dx, because we consider, normally when you consider a cylinder, it's pointing straight up, and this is the height, right? I have the radius here. But let's say this is our cylinder, and we turn it on this side so we can roll it. What we have is volume of the cylinder is pi r squared times h, which is dx. Remember, the dx will be like the h. Now, if we do this, we find the volume of this cylinder here. But suppose we cut this shape into several cylinders. Find the volume and add them all up. Now what we would have is the volume of the entire shape is the sum. Now from where to where? Let's say we start here at A and at the end is B. So it is the volume from A to B of pi r squared dx. Now let's consider the r. What is the r? If we consider any point from the center upwards, we get the radius. But the radius is the same as f of x, same as y. So, for example, if this was 1 and it was y equal x squared, this would be 1 squared, which is 1. If this was 2 and we find 2 squared, you go up, it will be 4. Alright, and so on and so forth. So, the radius here, when we have 2 for x, you go up to 4, the radius will be 4. So, that radius is the same as y for any particular value of x. So we can change this r squared to y squared. So let's erase that and put y squared dx. Now the thing is, we would not really get the perfectly accurate value for the volume, right? But suppose we cut this up into even thinner slices. The thing is, the thinner the slices, the more slices of solid that we would have to calculate, but the more accurate it would be. So what we want to do is make the slices so thin that the height, which you now could consider the thickness or the width, approaches 0. So the volume equal the sum from A to B of pi y squared dx. But as the limit of this approaches or tends to 0, right? If the limit of dx tends to 0, what we would have is the integral from A to B of pi y squared dx. In some cases you have a lowercase d before, but before you reach the approach towards 0, you may see examples where these d's are, for example, considered delta x, and then when it approaches 0 they change it to dx. Alright, but you get the idea. So the volume of revolution is the integral from the start to the finish of pi y squared dx. Alright, that is the general formula for the volume of revolution.